section 5.1, greatest common factor. Here's another section that we're going to take in two parts. In this part, we'll look at the idea of greatest common factor. In the next part, we'll investigate what's called factor by grouping. So let's talk about what we mean by greatest common factor. And understand that from this point forward, if you see the abbreviation GCF, you are expected to know that that stands for greatest common factor. I should not have to explain that again. Greatest common factor. Well, greatest means the biggest. Common means that they share. Factor means member of multiplication. In other words, something that will divide evenly into it. So if I want to know what is the greatest common factor of 24 and 30, what is the greatest common factor? What is the largest number that will divide into both that they share? Well, what are the factors of 24? Now, this is a skill that we talked about back in chapter 1, listing all the factors. Back in chapter 1, we listed integer factors. For this, I don't need the negatives, just the positives. And I said this is something that we will come back to and use again when we get into factoring. Well, it's that time. And so the factors of 24, I like to list these out as factor pairs. We know that 1 will go into 24 and 24 will go into 24, and that's always the case. 1 will divide any number, and the number itself will divide that number. 1 times 24 is 24, so that's a factor pair. Will 2 go into 24? Yes, 12 times, so there's another factor pair. Will 3 go into 24? Yes, 8 times. Does 4 go into 24? Yes, 6 times. Does 5 go into 24? No. Does 6 go into 24? Yes, but what? We've already discovered that. It's already in my list. And so we found all of the positive integer factors of 24. These are all of the numbers that will divide evenly into 24. Let's do the same for 30. Factor pairs, 1 and 30. We also have 2 and 15. I'm going to need a little more room than that. We also have 3 times 10. Will 4 divide evenly into 30? No. Will 5? Yes. 6 times. And will 6 go into 30? Yes, but that's already been discovered. So let's talk first about common factors. The common factors of 24 and 30, these are the factors of 24, those are the factors of 30. What do they have in common? They both have a common factor of 1. They both share the factor 2, as well as 3. What else do they share? A common factor of 6. And that's the only thing that they have in common between these two lists. Well, then the greatest common factor is going to be the biggest of those. Greatest common factor is 6. The largest number that will evenly divide into 24 and 30 is 6. Now, if the numbers get much bigger than this is not the best way to go about it. This is a good way to illustrate what I mean by factors, what I mean by common factors, what I mean by greatest common factor. We get an idea of what we're talking about, but it's not really the best method when we go looking for the greatest common factor of some numbers. So let's consider another way. First of all, do you remember what a prime number is? We're going to talk about prime factorization. A prime number is any number 2 or bigger. A lot of times people leave that part out. 2 or bigger, that is divisible only by 1 in itself. A prime number is an integer 2 or bigger that's divisible only by 1 in itself. So 1's not prime because it's not 2 or bigger. 2 is prime. The only things that will divide evenly into 2 are 1 and 2. 3 is prime. 4 is not prime because 4 is not only divisible by 1 and the 4 itself, but it's also divisible by 2. 5 is prime. Nothing divides 5 but 1 and 5. The next one is 7, 11, 13, 17, 19, 23. And you should know the first, dozen or so prime numbers. It turns out that there's no pattern to prime numbers that mathematicians have discovered at this point. There's still ongoing research into a very ancient idea in mathematics. So we memorize. Other numbers that are 2 or bigger that are not prime are called composite. 4 is a composite number, 6 is a composite number, 8, 9, and 10 are all composites. But numbers 2 or bigger, divisible only by 1 in itself, are prime numbers. Now that's important because what I can do with prime numbers is create unique factorizations. Let's consider just the number 30, and I'm going to put it over here because I want to talk about my 24 again in a minute on the left. What does it mean to factor a number? It means to write it as a product. 30 is 3 times 10, and that's factored. Somebody else might say, well, what about 2 times 15? Yeah, that's a factored form of 30. Well, what about 5 times 6? Yes. And what about 1 times 30? Those are all factored forms of 30. And so if I say factor that 30, we could all end up with different answers. And we know that in math we like to agree on our final answers. So one way to do that when I'm factoring a number is to insist that it is factored into prime factors. That is, we keep splitting it down until we have nothing but prime numbers. So let's consider. 30 is 2 times 15. Now 2 is a prime number, but 15 is composite. 15 can be broken apart again. I'll bring down the 2 because I can't split it down any further. And 15 is 3 times 5. 2 times 3 times 5. Those are all prime numbers, and when multiplied out, they give me 30. And if I ask you to prime factor 30, that would be your answer, 2 times 3 times 5. And notice that it doesn't matter how I start. I could have started by saying, well, this is 6 times 5. Somebody may start with 2 times 15, somebody else may start with 6 times 5. But by the time we get this completely broken down, 6 is 2 times 3, 5 is already prime, we're all going to end up with that same answer. Maybe not in the same order. Somebody else might have 3 times 5 times 2. But we're all going to have that same list of numbers. Let's prime factor this 24. One way to do this is 4 times 6, which is 2 times 2 times 2 times 3. All primes. I've prime factored the 24 and the 30 that we were talking about earlier, and I'm still wondering, what is the greatest common factor? When we made our list a minute ago, we discovered the greatest common factor was 6. What can these prime factors tell me about greatest common factor? Well, I'm looking for the biggest thing that they have in common. What do they share as factors? Well, I can see that they share a factor of 2. I can see that they share a factor of 3. And that's all that they have in common in their prime factorizations. The greatest common factor, then, is 2 times 3. In other words, put that back together, which is 6. And this is a much more efficient method, especially as numbers get larger. Now, what we hope is that In most cases, you will be able to just look at the numbers, the 24 and the 30, and just think for a minute. Just think for a minute. What is the biggest number I can think of that will divide them both? You think for a minute, you come up with 6. You can check that. If I were to divide both of these by 6, doesn't that sound like reducing a fraction? If I were to divide both of these by 6, here it would leave behind a 4. There it would leave behind a 5. Do 4 and 5 have any factors in common? In other words, if I ask you to reduce 4/5, is there anything you could divide out? No. And so 6 must have been the biggest thing we could divide by. So most of the time we're just going to look at the numbers and we're going to say, I know that greatest common factor. The biggest thing that will divide them both is 6. If we get stuck, we have this guaranteed method to fall back on. And that's what this is. This is a guaranteed method that we can fall back on if we get stuck. Let's do another one. Let's say I want to know what is the greatest common factor of 45 and 75. What is the greatest common factor? Well, I see they're both divisible by 5. Easily I see that. And now, if you didn't listen to me back at the beginning of the course, on your homework assignment sheet, in section 1.5, I had said, learn the rules from number 129 to 136, and those were your rules of divisibility. I'm not just saying that to give you busy work. We need to know these things. Well, she repeats it for you here at the beginning of this section, at the very bottom, in a table. Here are the rules of divisibility for numbers that are divisible by 2, 3, 4, 5, 6, 8, 9, and 10. If you want to know the rule for 7, see me sometime and I'll show it to you. It's a little crazy, but you practice it enough, you can actually do it in your head. We know a number is divisible by 2 if it ends in 0, 2, 4, 6, or 8. In other words, if it's even. A number is divisible by 3 if the sum of the digits is divisible by 3, and so on. You should already know these rules of divisibility. If not, learn them now. These are both obviously divisible by 5. And if you're up on your rules of divisibility, you should also notice these are both divisible by 3. 4 plus 5 is 9, which is divisible by 3. 7 plus 5 is 12, which is divisible by 3. If they're both divisible by 3 and both divisible by 5, they've got to both be divisible by 15, because 3 and 5 have no common factors. Is 15 the largest thing that will divide both of these? Is that the greatest common factor? If I get stuck, I can always start prime factoring. And I can break these down. Once I have them prime factored, I can look and see what they have in common. They both share a 3. They both share a 5. So yes, the greatest common factor, 3 times 5, is 15. If I get stuck, I can use prime factorization. Hopefully, the majority of the time, I'll be able to look at the numbers, ponder on it for a minute. And guys, when we're looking for greatest common factor, think of it like this. If I wanted to reduce the fraction 45/75 in a single step, yes, I could divide top and bottom by 5 and then go, oh, I also need to divide out a 3 and do it in 2 steps. But if I want to do it in a single step, what is the biggest number by which I can reduce this fraction? Turns out to be 15. That's the greatest common factor. If you can reduce that fraction in a single step and reduce it no further after that, that must have been the greatest common factor. If I get stuck, I have my method using prime factorization and collecting what they have in common. And this is what she describes in the blue box here at the beginning of the section. actually just above that table with our rules of divisibility here on page 330, finding the greatest common factor. And she describes this process. Let's do a couple more. What if I want to know the greatest common factor of 39, 52, and 65? What is the largest number that will evenly divide all three of those? Well, if I don't see it right off, or if pondering for a minute doesn't help, I can always start breaking these down. 39 is obviously divisible by 3. 3 times what? 3 times 13. Those are both prime. I stop right there. 52 is obviously divisible by 2. I think most of us would start with 2 times 26, and that's fine. Now, that's not how I started. Being a poker player, when I see a 52, I think about a deck of cards. And I know in that deck of cards, there are 4 suits of 13 ranks each. So yeah, it's 2 times 26, but I'm going to start with 4 times 13 because that is what comes to my mind. But in the end, we will all end up with a pair of 2s. Still sounds like poker, doesn't it? We'll all end up with a pair of 2s and a 13 in our final factored form. 65 is obviously divisible by 5. 5 times what? 5 times 13. I have all 3 of these prime factored. What do they all have in common? Only that 13. So if it's a situation where it's not obvious, I mean, for 24 and 30, I hope you can see that 6 without having to go through the process. But if you get stuck, you've got this to fall back on. Let's do one more. What is the greatest common factor of 14 and 15? Now think about it for a minute. Greatest common factor of 14 and 15. What is the largest number that will evenly divide into both of these? If I get stuck, I can prime factor. There, they're prime factored. What do they have in common? Nothing. What kind of nothing? We're talking about factors. We're talking about multiplication. We're talking about the multiplicative nothing. If they have nothing in common, then the biggest thing that will divide them both is the multiplicative nothing, 1. If nothing else, the greatest common factor has got to be at least 1. Every number is divisible by 1. Let's throw in some letters. What is the greatest common factor of x cubed, x to the 4th, and x to the 5th? Let me back up for just a minute. One thing I could have mentioned, what if I ask you to reduce the fraction 14/15? Can that be reduced any further? No. Why? Because the biggest number that will divide them both is 1. There's nothing you can do multiplicatively to reduce that fraction. Okay. Greatest common factor of these 3 terms. What is the largest factor they all have in common? Do all 3 of these have at least 3 x's in them? Yes. Do all 3 of these have at least 4 or 5 x's? Do all of these have at least 4 x's in them? No, the first term only has 3 to give up to begin with. So the greatest common factor, the biggest thing that will evenly divide into all of these, is x cubed. And so our rule for getting the greatest common factor when variables are involved is take the variable at its smallest power. All of these terms have 3 x's. Not all of these terms have 4 x's or 5 x's, but they all have at least 3. And so that's the biggest thing that they have in common. We take variables at their smallest power. Join me now in the homework. Number 14. We are asked to find the greatest common factor for each list of terms. And let's try to do this one by inspection. If we have to, we can always start prime factoring the numeric parts. The 60, the 70, the 90. But let's just think about it for a minute. Can you determine the greatest common factor among those 3 coefficients? What is the biggest number that will divide evenly into 60, 70, and 90? Well, it's the obvious one. It's the one jumping out at you. It's the 10. And think about that. If I were to divide each of these by 10, it would leave me 6. It would leave me 7. It would leave me 9. 6 and 9 have a common factor of 3, but do all of them have a common factor of 3? No. In fact, 7 is prime, and 7's not a factor of the other 2. In other words, if I were to think about this as reducing these 3 numbers down as far as I could, dividing by 10, getting them down to 6, 7, and 9, that's as far down as they'll go. If I get stuck, I can always prime factor and find what they have in common. And then the variable part. Do all of these terms have at least 4 factors of z? Yes. Do all of these terms have at least 8 factors of z or 9 factors of z? No. We take variables at their smallest power, z to the 4th. And there's my greatest common factor. Number 18. A similar problem, but a problem that comes with a warning. As we work it, we're going to discover we need to be very careful. We need to think clearly about what we're doing. Find the greatest common factor among these 4 terms. What is the largest number that will evenly divide 45, 75, 90, and 105? I happen to know from just moments ago that 45 and 75 have a greatest common factor of 15. Does 15 divide evenly into 90? Yes, it does. It'll go in 6 times. Does 15 evenly go into 105? Yeah, because that's just what? 15 bigger than 90. It goes in 7 times. Greatest common factor among my numbers is 15. If I get stuck, I can always prime factor and say, okay, 45 is 3 times 3 times 5. 75 is 3 times 5 times 5. 90 is 3 times 3 times 2 times 5. And 105 is 5 times, what's that going to be? 21, which is 5 times 7 times 3. What do they have in common? They all have a 3. They all have a 5. And that's it. So yeah, the greatest common factor among the coefficients is indeed 15. No doubt about that now. Now among the letters. We take our variables at their smallest powers. What is the smallest power on C? Right here, C to the 1st. And the smallest power on D? D to the 1st, so just D. That's wrong. will this term divide evenly into all four of those? Does every one of those four terms contain a 15? Yes, we've shown that here in blue. Do every one of those terms contain a factor of c? No. Right here, there's no factor of c. So what would that be? C to the 0, which is the multiplicative nothing, 1. Do all of these terms contain at least one d? No. My second term does not contain a d. So that would be d to the 0. C will not evenly divide all four terms. D will not evenly divide all four terms because all four terms do not contain at least one C, at least one D. Greatest common factor? Simply 15. We want to know what all four of these have in common. They all have a 3 and a 5, making that 15. Do they all have at least one C? No. Do they all have at least one D? No. So very careful. Very careful. Now let's talk about factoring. In this chapter, we're going to be factoring. You've heard the sermon in class. If you can't factor, you're pretty much stuck. Because almost everything beyond this chapter is going to rely on your ability to factor. So these first four sections, it is absolutely paramount that we get these down. Factoring is unmultiplying, just like my 30. I factored it, didn't I? I prime factored it all the way down into this factored form, 2 times 3 times 5, so I could see all the pieces that multiply together to give me 30. Well, then what would it mean to factor a polynomial? Think about this. If back in chapter 1 I had this problem, simplify 2 times quantity x plus 3. Well, I would distribute that 2. That would give me 2x plus 6. What did I do? I multiplied and I got this simplified answer. Well, factoring is like playing Jeopardy. I give you the answer, you tell me what the question must have been. Okay? I said simplify. The instructions here could have read multiply. We turn it upside down. The instructions now say factor. Factor this 2x plus 6. And I've got to break this back down into this 2 and that binomial. And the way I do that is by factoring out a greatest common factor. What is the greatest common factor between the two terms in this binomial? 2x and 6. What is the largest thing that will evenly divide them both? As far as the numbers go, a 2. As far as the letters, does every term here contain at least one x? No. So x is not part of the greatest common factor. Greatest common factor is 2. Well, if I pull that back out, if I undistribute that 2, in other words, if I divide each of these terms back by 2, where does it return me? If I pull 2 as a factor out of 2x, it leaves the x. And plus, if I pull 2 as a factor out of that 6, what's left behind? A 3. Factoring is easy to check. Distribute that 2 back in. Does it return you to the original factoring problem? And so, just like we factored our 30, we've now factored this binomial back into the original monomial and binomial that created it. That's factoring, at least one example of it. We're going to look at several different types of factoring. For now, for this lecture, we're going to look simply at factoring out the greatest common factor. Number 42. Now, for now, the instructions read, Write in factored form by factoring out the greatest common factor. After we're done with these 4 sections, I may give you this problem, and the only instruction you will see is factor. And you will recognize that part of factoring is to look for a greatest common factor. For now, she's holding your hand. She's saying, get this factored by pulling out a GCF. And so that's what we'll do. What is the greatest common factor between these 2 terms? Well, for 8 and 6, the biggest thing that will divide them both is 2. And as far as my variables go, smallest power on x is 1. Right here, you can't see it. Do both of these terms contain at least 1x? Yes. Do both of these terms contain at least 2x's? No. You take the variable at its smallest power, so long as it appears in every single term. But you've got to watch situations like number 18 with those C's and D's, right? The greatest common factor between these 2 terms is 2x. To factor that out is to unmultiply, in this case, undistribute. We're going to undistribute a 2x. If I pull 2x as a factor out of 8x squared, it leaves behind 4x. Right? Because when I multiply those back together, doesn't that return me to the 8x squared? And plus, if I pull 2x as a factor out of 6x, well, you pull a 2 out of the 6, it leaves a 3. You pull the 1x out that it's got, leaves no x's. Not sure about that? Distribute that back in and see if it doesn't return you to the original problem. And so this is factored. Look at number 50. Now, sometimes we use the term greatest common factor a little loosely. In number 50, notice our leading coefficient is negative. What we will discover is that when your leading coefficient is negative, it is almost always to your benefit to factor out that negative as well as the greatest common factor. A greatest common factor can never be negative, because its positive would also be a common factor. If negative 2 is a common factor between 2 numbers, well then positive 2 is also a common factor. And positive 2 is bigger. So when I say factor out the greatest common factor here, we're going to understand that typically, if the leading coefficient is negative, I want to factor out that negative as well. And we've got to watch our signs. We're going to factor out a negative along with what? Greatest common factor between 21 and 7. They're both divisible by 7. And obviously nothing bigger. 7 is 7. There's nothing bigger than 7 that will go into 7. And for my variable part, take the variable at its smallest power. Do both of these terms contain at least 2 b's? Yes. Do they both contain at least 3? No. Take it at its smallest power. Now we're going to undistribute this negative 7b squared. We factored out the negative along with the greatest common factor, because we discovered that when the leading coefficient is negative, this is to our benefit later down the road. So we're going to begin practicing it now. If I factor a negative out of a negative, it will leave a positive, right? I mean, when you go to distribute this back, you're going to have a negative times a positive to give you this back, this negative. So, if I pull a negative out of a negative, it leaves a positive. If I pull 7 as a factor out of 21, it leaves a 3. 7 times what is 21? 3. And if I pull 2 factors of b out of b cubed, it leaves 1 factor of b. Now, if I factor negative 7b squared out of negative 7b squared, well, I'm taking the whole thing. So what's left behind? Nothing. Oh, very careful. Does that mean close these parentheses and you're done? I don't think so. Multiply that back together. You're going to be missing a term. When I say it leaves nothing, what are we talking about? Well, this is a multiplicative process. Factoring is multiplicative. So it is that multiplicative nothing. It's the 1. If you pull negative 7b squared out of negative 7b squared as a factor, what's left behind? That residual factor of 1. Now check it. Now if you distribute that back in, you see that it returns the original problem. Again, right now her instructions say factor by pulling out the greatest common factor. Later down the road, my instructions will only say factor. Number 62. We're going to have a lot to keep track of here. Factor. And right now she reminds us that to factor is to factor out a greatest common factor among these terms. As far as the numbers go, it's obvious they're all divisible by 5, but is that the biggest number that will divide them all? Well, let me think about this. If I were to start factoring this and I pulled out a 5, and whatever, just ignore the A's and the Z's right now. We're just pondering, is 5 the biggest? What would get left behind? You pull 5 out of 125. 5 times what? 5 times 25 is 125. Some A's and some Z's. Plus, pull 5 out of 60 as a factor. 5 goes into 60 12 times. Some A's and some Z's. 5 goes into 85 how many times? Here's what I'm thinking. 5 goes into 120 times, which means 95 would be 19, which means 90 would be 18. 85 divided by 5 must be 17. And that runs through in my head very quickly, faster than I can write it. However you go about finding it, 5 goes into 85 17 times, some A's and some Z's. If I pull 5 as a factor out of all of these coefficients, do the numbers left behind still have anything in common that I missed? Was there something bigger I could have factored out? It's like double checking a fraction to make sure it's really in lowest terms. 25, 12, and 17. 17 is prime. And 17 is not a factor of either of the other two. So yes, I am confident that 5 is the largest. You can always prime factor, but what I just showed you is like checking a fraction to see if you actually got it in lowest terms the first time. If not, fix it. And if 5 had not been the biggest, we could have gone back and fixed it. So 5 is the numeric component of this greatest common factor. Now my variables. We take our variables at the smallest power. Are there A's in all 3 terms? Yes. And at the smallest, A is raised to the 3rd. All 3 terms contain at least 3 factors of A. And Z appears in all 3 terms. All 3 terms have at least 2 factors of Z, 2 being the smallest power on Z. Now let's factor out this greatest common factor. You pull a 5 out of 125, it leaves 25. Pull A cubed out of A cubed, leaves no A's in this term. Pull Z squared out of Z to the 5th, it leaves Z cubed. Plus, pull 5 out of 60, it leaves behind 12. Pull 3 factors of A out of 4 factors of A, it leaves a single factor of A. Pull Z squared out of Z to the 4th, it leaves 2 factors of Z, Z squared. And finally, plus, pull 5 out of 85. That'll leave that 17, because 5 times 17 is 85. Pull 3 factors of a out of 5 factors of a. Leaves you 2 factors of a, so a squared. And pull z squared out of z squared. Leaves no factors of z in this last term. In fact, when you factor out the greatest common factor, at least one of the terms in the parentheses should be missing the a. At least one of the terms in the parentheses should be missing the z, right there. Otherwise, you didn't get everything that you needed to get. And here we have factored out that greatest common factor. All right. Now, let me show you a very simple one. I'm going to work a problem and a companion problem. First thing I want to do is factor out the greatest common factor of 2xy plus 3y. How many terms do you see? There are 2 terms separated by that plus sign. Do these 2 terms have any factors in common? I've kind of highlighted it in pink for you, haven't I? They both share a common factor of y. If I factor out that y, it will leave 2x plus 3. Not sure? Distribute the y back in. It returns me to the previous step. What was the greatest common factor between these 2 terms? The only thing that they share in common is that y. 2 and 3, greatest common factor is 1, and you can't see a 1 if you pull it out. The only thing they had in common other than 1 was a factor of y. Now compare this to a companion problem. 2x times the quantity, a plus 1, plus 3 times the quantity, a plus 1. My first question, how many terms do you see? How many terms? Terms are separated by pluses and minuses unless the plus or minus is buried in parentheses. There are 2 terms separated right here by this black plus sign. The pink pluses are buried in parentheses. So there are 2 terms split apart right here. Now, do these 2 terms have any common factors? You see why I've used the color marker. I'm leading you to say yes, they do have a common factor of a plus 1. You will often hear me say they have a common binomial factor of a plus 1. And it's just like this problem. I could factor out the pink y. Over here, I can factor out the pink binomial. Factor out that a plus 1. And what gets left behind? The 2x plus 3. Now, understanding this concept is absolutely critical before going on to the second part of this section, which we'll do next time. I want to look at one more problem. Number 70. And in number 70, I want to tell you something that I might do just a little differently than she does in presenting this problem. Number 70, factor out the greatest common factor. The way she presents the problem, she shows a coefficient of 1, a factor of 1 in front of this binomial. I don't think I would. If I were to give you this problem, I wouldn't show you that 1. I would expect you to understand that there's an invisible 1 sitting there if you need it. All right? How many terms do you see? There are 2 terms separated by this plus sign. Those minuses are buried in parentheses. There's my only boundary. Do these 2 terms have any factors in common? Yes, they do. They have a common binomial factor of x minus 9. Let me put some color in here just to kind of highlight this common factor. We have two terms. They have a common binomial factor of x minus 9. I can factor out that x minus 9, just like factoring out this pink y. And what gets left behind? A y squared plus, and whether you can see this one or not, if you pull x minus 9 out of x minus 9, what's left behind? That residual factor of 1, that multiplicative nothing. Being able to work these types of problems where you have a couple terms with common binomial factors is absolutely critical to being able to do the next problem type, which is called factor by grouping, that we will look at in the next part. And so for now, you can do your homework up through number 69. Homework up through number 69. Next time we'll come back and we will build on this idea of factoring out a common binomial factor to be able to factor even bigger polynomials. And again, it is absolutely crucial that you nail chapter 5. So get straight to that homework. Start practicing right now. We have to have this factoring down pat if we expect to be able to go on beyond these first 4 sections of chapter 5.